Hello everyone, this is Dr. Vivek Kumar from Department of Mechanical Engineering, School of Technology, Pandit Deen Dayal Petroleum University, Gandhinagar. In the last video, I have described some activities related to concept testing in product design and development process. The concept testing has been performed for electric powered scooter, designed for commuters around the college campus and personnel working in the premises of a factory. In this video lecture, I will be covering some basics method used to perform concept embodiment activity in product design and development process. This flow diagram represents an alternative approach of product design and development process. Earlier, we have studied product design and development process in three stages, namely understanding the opportunity, developing a concept, and finally implementing a concept. This approach also incorporates all these features, but they are classified in two categories. First is the conceptual design and second embodiment design. In conceptual design, we perform sequential activities such as problem statement, that is the mission statement, identify benchmark products, quality functional deployment, project planning. The next step in conceptual design is customer need identification, concept generation, selection and testing. The outcome of the conceptual design is the product architecture, or we can say the final engineering specification of the tested concept. Now the next stage is the embodiment design. In this process, we will transform the product concept and architecture into physically realized system. The developed system must cater the specific need of the customers, as well as it should be robust enough to perform well under the different operating and user conditions. Operating conditions mean wider range of load, speed and environmental conditions imposed on the product. User condition corresponds to either ideal usage as per the manuals, which is generally done by the skilled user, or rough handling of the product by unskilled user or trainees operating the product or a machine. The product must be designed such that the likelihood of failure of the product is reduced to as minimum as possible. The concept design are often the mental images of a product, that is, how it will be architectured or specified and how it will be configured. The concept embodiment transforms the concept systematically and iteratively into process that allow fabrication and assembly of different components of a concept into a working form. The transformation, however, depend upon the initial description of concept provided in the conceptual design. In conceptual design, we started with some hand-drawn sketches, stick figure geometries to depict mechanism of a product. The final physical shape of the product is very fuzzy or unclear in the conceptual design. The clarity in this regard is provided by the concept or design embodiment phase of the product design and development process. Concept embodiment is a process where the structured development of the design concept take place. It is in this phase that the decisions are made on the strength, material, selection, size and shape of a product. Embodiment design is concerned with three major tasks, namely product architecture, design configuration and parametric design. Product architecture is concerned with dividing the overall design system into small subsystems and modules. In this step, we decide how the physical components of the subsystem are to be arranged and assembled so that they can carry out the functional duties of the proposed concept. Design configuration. In design configuration, we decide what are all features required in various parts or components of a product and how these features are to be arranged in a space relative to each other. Parametric design starts with information from the configuration design process. The aim of this process is to establish the exact dimensions and tolerances of the final product. The final decision on the materials and manufacturing processes are also done here if it has not been fixed in the previous processes. One of the important aspects of parametric design is to examine if the design is robust enough or not. The concept embodiment process can be carried out in two approaches, namely the basic methods and advanced methods. Both the methods start with overview and the context of concept, obtained after performing concept testing activities. Following overview and context, in basic method a concept is refined into final geometric configurations, material descriptions, manufacturing process to be employed to realize the concept in the physical shape. Then a embodiment checklist verification is conducted to ensure that all the function of the concept and engineering specification satisfy the customer need. In the second approach, that is also known as the advanced method, we use mathematical modeling, embodiment principles and failure mode and effect analysis to verify that the product and engineering specification of concept satisfy the customer need. These methods provide a more thorough means to ensure the robustness and integrity of the product performance. Product design and development team consist of multidisciplinary personnels coming from the technical and non-technical backgrounds. The concept embodiment task is associated with the engineers of the product design and development team. During this process, engineers carry out many activities such as selection of standard components, design and customization of specific components, developing component interfaces with the humans or users, material selection, geometric shape selections, dimensions and the tolerances of the different components, surface finish, selection of fasteners, connectors, manufacturing and assembling process for developing a particular product. In order to make such choices, an engineer must understand how the concept interacts with its environment. In this stage, engineers apply their mathematical and applied science knowledge to model complex systems that can be tested and refined as per the will of the engineer. Such knowledge will help the engineer in concept embodiment process. The methods used in embodiment of concept are based on mathematical and empirical modeling to estimate the performance and product life cycle. Modeling methods provided us the way to measure the performance of the product and ascertain the potential failure modes of the product as it is used by the customer. For example, design for manufacturing and assembly provide an approach through which we can enhance the reproducibility, availability and economic benefits of a concept. Physical prototyping method provide a means to test the actual performance and manufacturing ease of the product concept. Methods such as design for service ensures the minimum running and maintenance cost associated with the product concept. Design for environment. Design for environment assess the effect of product on the surrounding environment and sustainability of the product. The aspects related to life cycle of a product ensure that it can be maintained and ultimately reused and recycled. The aspects such as design for manufacturing and assembly, prototyping, design for environment will be discussed in details in the succeeding video lectures of this course. Before proceeding to the basic and advanced method in embodiment process, let us visualize how embodiment process gives a physical shape to any test concept. Here we discuss an example of bilge pump. Such pumps play a vital role in the operations of sea vessels, or you can say ships. They are also used daily as well as in case of emergency. After cleaning or repair work inside the engine room, some water or other liquid will run into the bilge valves. These wells are then emptied by means of bilge pump. As the water may contain oil, it needs to be cleaned before pumping over the board. Here are some examples of the bilge pump operated under pressure difference, operated by electrical energy, and also hand operated. Let us propose a concept for natural energy driven bilge pump product. Now we will cover entire process from understanding the problem to develop a concept to implement or embodiment of a concept. The first stage includes the customer need analysis, functional modeling and product architecture layout, that is specification through mission statement. At this stage, visualization and embodiment of concept is very unclear, or you can say in physical form, in our mental images, it is very fuzzy. The product is understood in terms of the generic black box function requiring some form of energy to deliver water or fluid to the environment. Further functional decomposition is performed to specify primary and secondary functions of the main function of the concept. Here, the economic opportunity of the product is understood and engineering specifications of the product are investigated and documented. In the next stage, concepts are developed as sketches or line diagram with not detailed but a good level of geometric descriptions. Here the focus of the process is to synthesize the design or the concept but not to analyze it. Detailed information such as geometry, configurational, shape, materials, etc. are unknown in this phase. The mental image of the concept becomes more focused, yet fuzzy nature of the concept specific to elements or mechanical components remains there. The last stage is concept embodiment. Here all the issues related to geometry, shape, configuration and materials about the product concept are resolved. This process involves thousands of decision making and iterations. Hundreds to thousands of parametric decisions depending upon the scale of the problem are taken. All these choices or decisions in this stage can be probably change the shape and configuration of embodied concept. In this stage, decisions are taken such as what material should be used for different component of pump such as ball valve, strainer, etc. What are possible mode of failures occur in pump such as corrosion, water backflow, etc. How do we configure the pump interface to operate it? Type of fasteners, hoses to be included in the design. How to design the pump for ease in manufacturing and assembly. Process embodiment is the answer to all these questions and other questions which occur during the specific stages of product concept development. While developing a robust product or family of products, two issues drive the concept embodiment. These are refining product geometry and system modeling towards detailed design. Three design scenarios occur in such case, which are original design, adaptive design and parametric design. In original design, a significantly new technology are introduced in the S-curve. For example, introduction of friction disc in braking system. Adaptive design goes with some modification in subsystems such as induction of ABS in existing braking system. Parametric design deals with changing geometric parameters and materials while retaining much of the original design. The concept embodiment is much more complex while dealing with the original and adaptive designs. Still, while performing the concept embodiment in all three types of design, we require detailed drawings, exploded view, assembly drawings, tool and manufacturing processes, tolerances, etc. in the complete process or to complete the process. Embodiment moves the concept iteratively towards a definitive form which include geometric layout, material composition, quality and manufacturability issues, and economics. The embodiment process is challenging as parameters in a product containing multiple subsystems are coupled with each other. A change in one parameter such as geometry or material may affect the performance parameter of other systems within the product. This means design of all subsystems go parallel with each other, unlike in the concept development phase. This requires a great deal of iteration in decision making and selecting component of subsystems. The general procedure to refine geometry and layout of a product from an abstract form to concrete form was provided by Paul and Bitts in 1996. The process is completed in three phases, namely concept generation as discussed earlier, preparing initial or the rough layout to preliminary layout. The process begins with considering product specifications. Then critical needs are identified that will drive the embodiment process. These are size determining specification, arrangement determining specifications, and material determining specification. After this, overall layout of the product is drawn to a scale based on rough concept drawings. In these drawings, specifications and maximum dimensions of a product and clearance between the relative subsystem, installation path, and general arrangement of the concept with respect to each other are depicted. Once the rough sketches are completed, now the main functional of concept product which we have already identified using the fast or subtract and operate techniques are verified using the concept drawings. If a function is common to two or more subsystems, then it must be simplified here. By now, the range of parameters for geometry and material properties are established. Based on these ranges, components or sub-assembly of the product are searched in available market as standard or customized products. The sub-process concludes by choosing effective layout from the various alternative layout Using functional decomposition, additional functions should be determined which may be falling under supporting or auxiliary functions. Auxiliary functions came into picture due to implementation of original function. For example, a battery pack is selected to supply power to a subsystem. Now, auxiliary functions have to be implemented to hold the battery pack into the system and to route the power supply to different sub-assemblies of the product. Incorporation of main, supporting and auxiliary function produces the rough layout of the product. Now the rough layout should be detailed, ensuring the compatibility of all sub-assemblies and their interfaces with respect to each other. This is done by the use of available standards, mathematical models, design guidelines and experimentation. In addition to this, the product should be evaluated for customer needs, robustness, safety and economic criteria. Now the developed layout should be checked to estimate potential faults, tolerances and clearances for product accuracy and repeatability. The embodiment process concludes with testing of physical prototype. The product layout is revised based on the results from prototype testing. Afterwards, the final layout and documentation of the product is prepared. Embodiment checklist is a basic method used to supplement and improve the overall embodiment process. It provides a systematic approach to apply design principles to the product development process. The checklist is created from the generic design principles such as robustness, clarity, simplicity, and safety in the product. Robustness minimizes the variation in performance of product under all expected environmental and user conditions. Clarity ensures all functions of the system or subsystem should be specified very clearly. Unintended functions such as noise and vibration should not be present or minimized in the system. This ensures that the performance of product should not be deteriorated or compromised with respect to presence of unintended functions. Simplicity refers to minimization of information content within a product design. Component shapes must be simplified as possible for ease in the manufacturing and cycle time. Number of the components should be reduced to as minimum as possible, provided that the product to maintain its satisfactory performance level. Safety. This design principle minimizes the risk created by the use of the product. This principle should consider strength, reliability, environmental effect, ergonomics, and accident-prevent aspect of using a product. Based on the design principles, that is robustness, clarity, simplicity, and safety, a checklist should be prepared by the design and development team. An example of embodiment checklist is shown here. In embodiment checklist, questions are asked specific to embodiment heading given in the first column. It is used to check the engineering specification of a product through a series of questions falling under the 4 design principle category. A mathematical model or a physical prototype is often required to measure the performance of product. The performance of the product is verified according to the questions set in the embodiment checklist. Once the product satisfactorily answers all these questions mentioned in the second column, the product layout is considered to be final for the development phase. Let us take an example of radio-controlled RC toy car. The car is electric driven and can emulate a full-scale on and off-road vehicle on a small scale. The speed and the steering of the car is controlled by a transmitter and it is powered by cell batteries. Let us apply the embodiment checklist presented in the previous slide to this car. One of the questions asked under heading layout, geometric and material is, does the chosen concept ensure freedom from resonance? This is an important consideration in a toy as well as full-scale car model, as many components of car such as bearing, shaft, helical springs or suspension system is subjected to vibration. These vibrations may lead to a resonance if it is not controlled. The tires, bearings and drive shaft in such a case can be mathematically modeled as a simply supported beam subjected to rotational motion. Failure in such case occur when the shaft speed approaches the critical speed of the system. The critical speed is a function of the length and the cross-sectional properties of the shaft, and it is determined using this expression. Here omega CR is the critical speed of the shaft and delta is the static deflection calculated using the theory of bending of the beams. The critical speed is found to be around 3600 rpm for the layout under consideration. The maximum driving speed in manual is around 2500 rpm. Based on this analysis, if maximum driving speed approaches in the vicinity of 3600 rpm, that is the critical speed of the system, we need to modify the layout, and the layout can be modified by increasing the shaft diameter to satisfy the safety concern mentioned in the checklist. Likewise, a mathematical model or prototype testing can be performed for each embodiment heading mentioned in the checklist. This is done before proceeding with the full-scale development and production of a product. With this example, I close the session on basic methods of concept embodiment process. If you have any queries, please write in the comment section. In the next lecture, I will start with advanced method, that is system modeling and failure mode and effect analysis for the concept embodiment design process.